When you hear the phrase supercapacitor, what comes to mind? Maybe a really big capacitor, or one that's just made really well, or a superhero. Yeah, okay, well what should come to mind is an electric double layer capacitor, or EDLC. These devices have very high capacitance and can replace batteries in some applications. In this video, I show what an EDLC is, a few important characteristics to know, and I have a demo where we harvest solar energy with one. Overall, my main goal is to explain why you cannot just stick 10 farads on your voltage rail and call it a day. So, welcome back to Workbench Wednesdays. My name is James, let's go charge. This video is sponsored by Eaton. They have a full range of supercapacitors with coin cells, traditional looking small cylinders, a hybrid style, large can cells, and modules. Modules are neat because they are series and parallel combinations of the large single cells, which can get up to 500 farads at 16 volts. Again, farads, not milli or micro. Now in this video, I am focused on the traditional cell style and how we can use it to replace a battery in a small Wi-Fi device, but many of the considerations I bring up apply to the other styles. Supercapacitors, or more correctly, electric double layer capacitors, have electrodes electrically connected by a liquid electrolyte through a mechanically separating material. That electrolyte contains positive and negative ions, but notice that there's something missing. There is no dielectric. Instead, when an electric field is applied, the ions are attracted to the electrodes. However, a thin interface called the Helmholtz layer forms between the non-soluble electrode and soluble ions. This layer is non-conductive like a dielectric. Now, as the capacitance equation shows, this ultra-thin dielectric layer means more capacitance. One trade-off with a thinner plate is the working voltage is also much lower, which is one reason individual supercapacitor cells are only rated for a few volts. And since there is a Helmholtz layer on both electrodes, guess where the double layer part of their name comes from? Those layers are typically symmetric, but asymmetric also exists. Combining them works like capacitors in series, it reduces the total capacitance. And just like with regular capacitors, putting EDLCs in series achieves a higher working voltage at the cost of capacitance. Now of course, you could put those series caps in parallel and create a bank. But if you do that, you need to consider how to balance the cells. By the way, as I mentioned earlier, supercapacitor modules are already series parallel combinations. One advantage of these off-the-shelf modules is that they usually have a passive or active balancing system built in. Oh, and I briefly mentioned the hybrid style. These are built different compared to the other cells. Hybrids effectively have an electrode that gives them properties similar to a lithium battery. So you end up with a small battery combined with a large EDLC. The advantage is a higher working voltage than a supercapacitor and more lifetime cycles than a battery. Now, the rest of this video covers the non-hybrid supercapacitors, which all store energy electrostatically like all capacitors, but with a little help from Helmholtz. So, can you just connect a supercapacitor to your 5-volt rail and go? Well, no, I already said you can't, but let's go see why next. Here are some Eaton HV series EDLCs. The 10 farad capacitor can handle pulse currents up to 10 amps and continuous currents of 3.3 amps. It is rated for 2.7 volts. When I apply that voltage, we can see it start to charge. Speeding up the video, it took about 50 seconds to reach 2.7. Let's talk about a few things. First, on the scope, the yellow is the voltage and the orange is the current. Notice how the current was maxed out until the supercapacitor's voltage reached 2.7 and then it rolled off. Like all capacitors, when an EDLC is discharged, it's effectively a short. And while supercapacitors can handle a high amount of charge and discharge current, you have to think about what is supplying that current. A bench power supply like we just used can self-limit itself until the voltage goes up, but not all sources can do that. Later, I have an example of that. Next, even after sitting for a minute or so, notice the capacitor is at 2.7 volts, but still drawing several milliamps of current. This is called leakage current. It takes hours for this to drop significantly. Related, when I turn the power supply off, the voltage immediately starts dropping, which is called self-discharge. Basically, both are related to the ions moving around in the electrolyte, and it takes them a while to settle down. For example, I left this cap sitting for 7 hours only connected to my test equipment. This graph shows the discharge curve, and at about 1000 seconds or 15 minutes, the voltage dropped 12% down to 2.35 volts. and after 3 hours, the cap lost about half its voltage. Seeing this voltage is important because voltage is directly proportional to the energy stored in the capacitor, which is calculated with 1/2 CV squared, where C is capacitance in farads and V is voltage in volts. Applying that equation to the supercapacitor's voltage over time, you can see how small drops in voltage means significantly less energy available. Leakage and self-discharge means losing some of that stored energy whenever the cap is not charging. Now, batteries do have a similar problem, but it's not quite as pronounced. However, their ESR is much higher than most supercapacitors. And speaking of ESR, it is something that is affected by temperature. As the EDLC's electrolyte gets cold, the ions become less mobile, causing the ESR to go up. However, as they get warmer, the ESR can go down. Now, ESR is important because it makes wasted power during both charging and discharging, which, when energy harvesting, losing energy during the charging phase could be just as critical as the discharge phase. Now again, temperature affects batteries as well, and in some cases, their ESR losses are even worse. Okay, now that we're talking energy, let's calculate how much energy we can actually use. If we have a fictional 5 farad capacitor charged to 3.3 volts, it stores 27 joules, and with 5 volts, it stores 63 joules. But real 5 farad cells are only rated for 2.7 volts, so we would need to put 2 in series to get to 5 volts, which means we would only effectively get 2.5 farads. Now, to find out how much energy your device needs, you need to know the voltage rail, the current draw, and how much time your device draws that current. For example, let's say we have a 5 volt device drawing an average of 50 milliamps for 10 seconds. That means it consumes 2.5 joules. Now, if we charge our real 2.5 farad capacitor to 5.3 volts, it would store 35 joules. Well, two things. First, that equation assumes that the current draw on the rail voltage is constant, which it isn't. But for the moment, it's a safe assumption. More importantly, it assumes you can discharge the capacitor to 0 volts, but you can't. I mean, you can, but you can't. Here's why. Let's consider a Pi Pico. The DMM on the left measures its input voltage, and the DMM on the right measures its onboard boost buck converter. When the input drops below 1.8 volts, the 3.3 volt converter shuts the Pico down. This point is known as the device's dropout voltage, which means once the supercapacitor's voltage drops below that level, we effectively cannot use its energy anymore. So our equation should have accounted for the voltage drop like this, meaning we would have just a few joules that we cannot use. The important takeaway here is that you might need to do something special with your circuit, like use a boost buck converter to squeeze every last joule you can out of the supercapacitor. Don't assume that the full charge is always available for your circuit. Okay, now let's go do something practical with the sun, or at least what I call the bald sun. Let's use this solar panel to charge up these supercapacitors to provide energy for this Pi Pico. And why are there 2 EDLCs in series? Because they're only rated for 2.7 volts, and I want 5 volts for the Pico's onboard regulator. The Pico is running the same code that we used in the Pico W power consumption video. There we saw 1 cycle of sleep, measure, and sending an MQTT packet consumes an average of 45 milliamps over 15 seconds. That works out to be 3.54 joules. And from the previous section, we calculated the usable energy in a capacitor is 31 joules, so we should be able to cycle the Pico up to 8 times. However, don't forget to add some margin for self-discharge, temperature shifts, and cloudy days. So let's say 5. Now, I know I'm sort of hand-waving some of the math here, but let me know over on the Element 14 community if you have any questions about these equations. This basic solar panel is rated for 200 milliamps at 5 volts. But in reality, putting my light right on the panel and measuring its output current with an electronic load only gets about 40 milliamps. But let's see what happens when it's connected to the capacitor. The bench DMMs are measuring the voltage and current from the solar panel. When I activate the bald sun generator, we get 250 millivolts and 50 milliamps of current. Wait, what gives? So this video isn't about solar panels, but when you want to harvest energy, it is very important to understand how your source operates. Long story short, solar panels need a specific load current to get a specific voltage to achieve maximum power. And as we saw earlier, supercapacitors are a dead short when they are discharged. So we need a circuit to limit the charge rate of the supercapacitors, which this little board does. It has an EDLC charge controller going to two 5 farad capacitors in series. By the way, that board did not come with Eaton supercapacitors, so I swapped them out for some Eaton HV series in place of the originals, for obvious reasons. Now with this charge controller, we can see that the solar panel drives about 60 milliamps, and we can see the supercapacitor's charge is building up. But now we have to wait. Keep this initial charge after full depletion in mind when deploying a solution. How are you going to recharge it? Or can you tolerate how long it takes to become operational again? At a minimum, you probably want to have a circuit to keep the microcontroller disabled until the capacitors reach a certain voltage. I did not do that, so I just kept the Pico disconnected until the caps were fully charged. Now that the caps are fully charged, you can see when the Pico activates, the cap's voltage starts dropping. The green DMM is measuring the supercapacitor voltage, and the yellow is watching the 3.3 volt boost buck regulator on the Pico. Let's look at my laptop to understand what it's actually doing. On the left is a MQTT client watching for the temperature message over Wi-Fi, and on the right is the supercapacitor voltage being streamed by Bluetooth from the green DMM. Turns out you can tell when the Wi-Fi is active because the voltage suddenly drops fast due to the higher current draw. And then a few seconds later, we see the MQTT message come through the broker. Now, right now, both the supercapacitor and the solar panel are providing energy for the Pi Pico. Let's see what happens when the sun goes down. As expected, the solar panel is no longer recharging the supercapacitor, and the Pico is just sipping away at that stored energy. I left the setup running until the 3.3 volt regulator shut down, and we ended up with 5 cycles from the energy stored in the supercapacitors. Now you know why I rounded down to 5 earlier. Okay, there's a few obvious improvements we could do. First, we should be using a proper solar tracker circuit to get maximum power out of the solar panel. Next, sending the temperature every few seconds is overkill. And if the Pico was monitoring the charge controller, we could change its transmit interval based on the condition of the supercaps. We could also add more capacitance. But let's just review what this demonstration actually shows. Overall, we have an effective setup to log some data, talk to the internet, and power it all with harvested solar energy thanks to an Eaton supercapacitor. One thing I did not mention is that supercapacitors do have a cycle count, but unlike batteries, it is hundreds of thousands of cycles. Whether you use coin cells, cylinders, or modules, supercapacitors are a viable alternative to some battery-based applications. Consider the amount of energy you need, how you will recharge the capacitor, and how you're going to manage its charge. In the show notes on the Element 14 community, I put some links to tools from Eaton, including a web-based calculator to determine how much cap you need. Plus, there is a list with all of the equations that I showed in this video. Remember, that is the best place to ask me questions because I get notified and then I can answer them, sometimes with more equations. As always, thank you for watching. For now, it is time for me to get back to fighting voltage droop with double layer charge on my electronics workbench.